Sure, sir. A very good morning to one and all. I, Dr. Neha Kapoor, welcome all the delegates to the Popular Lecture Series 2021-22, sponsored by Soft Material Research Society, Jaipur, jointly organized by School of Applied Sciences and Center for Renewable Energy and Storage, Suresh Gyan Vihar University, Jaipur, Rajasthan, India. As I heartily welcome our speaker of the day, Dr. Shrikant Saini from Kyushu Institute of Technology, Japan. As today marks the first day of commencement of Popular Lecture Series 2021-22, first of all, I would like to invite Professor Dr. Gaurav Sharma, Principal School of Applied Sciences, Suresh Gyan Vihar University, to deliver the inaugural speech. Over to you, sir.
Thank you, Dr. Neha. Am I audible?
Yes, sir.
Thank you. Good morning and welcome to all the delegates, research scholars, and my dear students attending this popular lecture series. At this moment, first of all, I would like to extend my sincere thanks to all the eminent speakers for accepting a keynote speaker for these lecture series. It's an honor and a privilege to have you all with us. Kindly accept my warm regards and humble welcome to this lecture series. Though we as a community are put to corner by COVID crisis, but still we stand together to make all the efforts to come out of it. Sharing knowledge and experience through digital platform is an attempt to reach to the masses and connectivity in this period. We at School of Applied Sciences, Suresh Gyan Vihar University, Jaipur, are continuously working to maintain the continuity of knowledge sharing to the students and scientific community by such lecture series and interactions. And at this moment, now I would like to take the opportunity to welcome our today's guest speaker, Dr. Shrikant Saini, sir, from Kyushu Institute of Technology, Kyushu, Japan. Welcome, sir. Today's webinar will give you insight about an interesting topic of thermoelectric materials for energy harvesting. And I'm sure that this topic is, the speaker will give you a deep insight of this topic, and you will be definitely enriched by this lecture. I once again welcome you all, and not taking much of your time, I would like to request Dr. Neha Kapoor to please take this session ahead. Thank you, ma'am.
Thank you so much, sir. Taking the session ahead, I would like to invite Professor Dr. Ankur Jain, Coordinator, Center for Renewable Energy and Storage, Suresh Gyan Vihar University, Jaipur, for the welcome speech and briefing of the lecture series. Over to you, sir.
Thank you, Dr. Neha. Very good morning, everyone. As a convener of this popular lecture series, welcome all the students, research scholars, researchers, as well as faculties from different universities, institutes, and research centers across the globe. As Professor Gaurav mentioned, that we are still facing the pandemic situation and looking to fight with the new corona variants every day, right? So during this difficult and challenging time of last 2 years, several positive things also happened. One of these is that we have learned several new ways to spread and share the knowledge with each other across the globe without meeting with each other. One of this method is to use online platforms for organizing these conferences, webinars, and lecture series. I am happy to share that Suresh Gyan Vihar University, Jaipur, has also adopted and developed these methods quickly and very nicely. As another attempt, we are now planned this popular lecture series in hybrid mode that is jointly organized by the School of Applied Sciences and Center for Renewable Energy and Storage of Suresh Gyan Vihar University, Jaipur. As coordinator of Center for Renewable Energy Storage, I would like to emphasize here that energy is one of the important human needs that decide the overall growth and environmental quality of our planet. So our center is working actively to develop new methods of energy generation as well as efficient storage of it, with a particular focus on solar energy, hydrogen energy, and lithium ion batteries. This lecture series is an attempt to connect the basic concept and actually the basic concept and the principles of physics and chemistry with the energy needs and recent develops using these principles, right? So we have in this lecture series, we have four eminent speakers. The first one is Dr. Shrikant Saini from Kyushu Institute from Japan, Dr. Dayanand from National Cheng Kung University, Taiwan, Dr. Vaibhav Kulshrestha from CSIR, CSM, CRI, Bhavnagar, India, and Dr. Manoj Kumar from MNIT, Jaipur, India. I hope that the coming month will be a month of knowledge, and these four lectures of this series will enlighten us and update our existing knowledge. Especially the young students from our institute as well as from other universities will surely be benefited and learn about several new fields. I once again welcome our esteemed speakers as well as all the participants. Thank you very much. Over to you, Dr. Neha.
Thank you so much, sir. Moving further, I would like to introduce our speaker of the day, Dr. Shrikant Saini. He is currently working as assistant professor at Kyushu Institute of Technology, Japan. Dr. Shrikant Saini has obtained his PhD degree from Jeju National University, South Korea. He worked as MRSEC postdoc fellow at University of Utah, USA. He obtained many recognitions like JST Researcher at Hiroshima University and Institute Fellow at Muroran Institute of Technology. His research is focused upon development and characterization of thin film of energy materials, especially thermoelectric and superconductors. He has more than 40 research papers to his credit in the journals of international repute. He has also authored many books and book chapters along with one patent. He has contributed significantly in many national and international conferences also. Today, Dr. Shrikant Seni will be talking about thermoelectric material for energy harvesting. So without taking much of time, I would like to invite Dr. Shrikant Seni to take the session ahead. Over to you, sir.
First of all, thank you everyone. Thank you, Professor Ankur, for giving me this opportunity. Unfortunately, today morning I have a little bit fever, but there is no such thing to worry. So I hope my energy level should be good enough to present my best. So let's start it. Let me share my screen. All right, is it visible? Okay.
Yes, sir, it is visible.
All right. So yes. So once again, thank you everyone, and thank you for a very kind introduction about me. So I will start today's presentation. What topic we have chosen here is about the, let me get familiar with this ones. Okay, so the topic for today's work, which I'm going to show you or introduce you, is kind of a thermoelectric materials for energy harvesting. So, of course, there are many things, many energy harvesting approaches work, which we will learn during the process of the presentation. We will see what other possibilities and why actually we are working on the thermoelectric material. And today's topic will be more towards the engineering side, where we will understand how the device fabrication happen and how actually we make the device and measure these devices at the standard of our lab or the laboratory standards. And then further you can proceed it for the industrialization of these kind of devices. There are devices which has been made in our lab and work in the industry at the moment, but those are the different, which I will be talking here is the latest, which is going to be the next generation devices using the material which are known for the solar cell materials, or which are known for the energy harvesting towards from the solar cell application. But we will be seeing those application combining with the thermoelectric materials. So today's Okay, yeah. So today's outline will be, I will be talking about the introduction and thermoelectric effect, what effect it is actually, and what we are seeing for generating the energy here. We'll be seeing the key parameter and their approaches, and we will be discussing about the various materials, and finally we will be having a quick summary and an open question, which direction should we going in the future. That is good for the future researchers who are planning to work towards in this field, particularly for the energy harvesting. So starting from the introduction, so this is a very common graph which you have seen for the most of the energy talks or the energy materials where we discuss about it. This energy diagram shows how the extraction of the fuel cell is happening year by year and where we are leading towards it, and the energy of consumption in the world, how much we are taking the energy in our daily life. This is one of the graph, and if you see, the increase is very fast, but there is a time going to be sooner or later where the extraction of the fuel cell will reduce. There are various reasons of that. One of the reason which is commonly known or understood is as a like finishing of these fuel cells or extraction from the core earth. So these are the one of the common reason what people think. But there is one more reason is we are developing on the many alternate energy sources. These energy sources will replace the traditional approach of getting the energy and using those energies. So where this replacement is coming in the picture in our case. So if we see very small example of this home, which is supposed to be like our home, which is the before, where you connect everything with the plug and you have connected and different kind of remotes you use, and different kind of light sensors they have been used, but those are all are connected with the power port and you are controlling them from there. But the era is moving, or the things which we are leading towards is the Internet of Things, where you have the devices and those devices are mounted on your desirable things or desirable approaches, such as the home light to the pets, and you have a car, even the car, and keeping a monitor in the home, including the monitoring the old people which is there. So this can be used in the medical approach as well as for the security point of view. Those all devices will be controlled by the portable device such as mobile or the laptop. That means we need an energy source which can be able to connect these two together, either from our pocket. For example, one of the example is if we make a wearable device and we want to see how much is our body temperature at the moment. In that case, you need to stick the device and that will sense and send the signal to your phone and you can directly see it there. For those particular amount of the work, the energy consumption is very less, and those all devices and the approach comes into under the category of Internet of Things. This is a one very small example, and the picture which I am showing you here is the latest or the state of art appliances and the home, where everything is controlled by the portable device such as your mobile phone, tablet, or PC, whatever you consider in that case. Now these devices are increasing day by day in the billions, and already it has surpasses the population of the human on the earth. And if on the other hand, if we see the penetration of these devices in the market is slower than what we are, what researcher or the people are expecting in this case. So why is the reason why the penetration of this market is slower? One of the reason what researchers has find out is because of the energy source or the source which we are using in this has issues, or better word say inconvenient. So those are the problems which we are facing, and the penetration is going a bit slow than what expecting was supposed to be the higher. So what need, if you consider, for example, you need an energy source for making any device. So for making us energy source, one of the basic requirement which we all are working towards, it should be sustainable. I mean, once you install it, it should not harm the atmosphere. It should, once you install it, no need to worry about it, and it's sustainable. It goes longer and longer on the time. And the second approach which we can understand is it should be easy to fabricate or easy to use, right? Otherwise it's very difficult to use such kind of things. And the important thing as a point of view from the customer side, it should be economic. I think we are able to afford it. And from the point of view of the engineering, it can be able to produce on the large area. So if a very small question, why large area is so important, why everybody talk about the large area production. So if you see this kind of devices, which is the flexible and can be made, if you produce this in the large area, so your total production cost goes down. And once you have a big area, suppose a 1 meter square you have an area, you can cut it accordingly, cut it different shapes, and use the device what actually you want, right? So this is the engineering point of view. Large area production is important in these kind of devices. Now, if you consider all this, already there are some sources which is the sustainable and existence is there, and we are using in the daily life, like a solar cell, solar heating panel, wind energy, biofuel. There are many approaches and many things which we are actually using, but these all have somewhere some drawbacks. For example, in the solar panel case, the panel gets dirty, you need to supposed to clean it, either it's the self cleaning or artificially cleaning or the cleaning by the force that required to do that. For example, and for example, the hydropower, in hydropower case, of course, it's sustainable, easy, but need a big production and the big area to put it where you have a resource for the water. Wind energy, the installation approach is very different, and the places where you install is a different. So there are some drawbacks behind that, but there is a one energy harvesting source which can be used in the robust condition. I mean, which condition these energy sources cannot be used, what I summarized here, where you can use easily the thermoelectric material or the thermoelectric energy harvesting. In thermoelectric energy harvesting, you have a two type of semiconductor, which is a P and N type. You heat one side of this material and the other side you cool it down, or you work as a heat sink, and then you flow the, and you get the potential drop from here, and when you connect the external resistance, you flow the current. So that's how the thermal electric energy harvesting is possible. So let's go a bit deeper in thermoelectric harvesting, what it is and how does it work. So what is thermoelectric effect? So as reported quite early, like almost I think it's 100 year already has been nearby. So in the thermoelectric effect is when you have a material which is a one side is a hot, other side is cold, which where you have a delta T is a temperature gradient, you get a delta V, which is the induced voltage here. This effect is known as the Seebeck effect, which we will use as an energy harvesting point of view. There is another approach, which is the reverse of this, which is known as the Peltier effect or the Peltier cooling effect, which is basically used for the coolers. That is, if you apply a voltage across this kind of material, one end become hot and another become colder. And this cold side, you can easily use to cool down the things. So there is a very recent product has been launched from the Samsung, is known as the thermoelectric Peltier cooler. So those coolers is a small refrigerator, but the excellent thing about it, once you plug in, there is a no sound in that. It's a sound, zero sound, because if you see example here, the thermoelectric effect and the Peltier cooler, there is no mechanical movement in these devices. That means if you just click the button here or put the plug in, you start cooling the surface what you want. But this is not the topic today what we are discussing. We are discussing about the energy harvesting, which is here. What means here you have a device you ready here and you start heating this device. Once you start heating this device, you generate the power, which is known as the thermoelectric uh, energy generation. So this is what we will be talking about today. But this is one example which I give is about the industrialization of recent approach from the Samsung, which they make the refrigerator excellent and beautifully. And it's really nice. I have experience about it. So so I will be talking today about the energy harvesting, which is thermoelectric energy harvesting. So where actually we use these devices. So one is a very small example is in the deep space or the places where the solar panel cannot work, or they have like due to the surface dust, and the other thing is the criticality, or you need a longer working time for the energy harvesting. And the deep and the robust condition thermoelectric materials works a lot. Even the Roser from the NASA is a curiosity. They also using the thermoelectric energy harvesters for generating the electricity in case of analyzing the data over there. This is the one example. Second example, as I showed you, the flexible device which we can make and we can wear it. The one of the third example, which is a very important, which we are also working towards this, is the exhaust engine or the exhaust pipe in the automobile. Here, when the heat comes out here, this heat temperature you can use actually to produce the energy, and that can reduce the cost of the use of the petrol or the gasoline, whatever you use there. So that can be easily works in that point of view. So that is one of the energy harvesting in this. Apart from this, which I have not shown here, but probably I will show you later. Suppose you have a big furnace or the big chimneys where you are working, or the steel plants, their temperature is very high, and there's a lot of waste in the material or in the process happen. Those kind of waste also can be used for the energy harvesting. One very small example I will give, I think I forgot to put the picture here. When you cook in a home, so you are using a pan. Between the pan and your gas range, what you're using, the gas fire, the temperature difference is about 400 degrees C. That temperature difference can also be used to generate the electricity. That can work in the robust condition, like suppose in the hiking or the places where there's no electricity, or the outdoor activities where you can cooking, meanwhile you can charge your mobile phone. That is one of the approach of using that kind of material and that kind of devices. Now in the flexible, which I was talking about, which is the main topic of my work, is a wearable electronics. These kind of patches we wear, and this have energy source, energy module, or the energy source we mounted here. So how does this energy source work? So our body have a temperature, and the outside temperature is different than the body temperature. That temperature difference generates the electricity and send the sensor signal to the phone or the whatever portable device we are using in that case. And this sensor or sending the device required actually very less power, because mostly if you notice, the phone is always either in the hand or in the pocket. So that means it's very close interaction, and easily you can transport those kind of power, and minimum power approach you can use and transfer this kind of signal in that case. So this is my main topic, which we'll be discussing later, these kind of materials. Now we understand what is thermoelectric, we understand where you use it, we have an idea. I did not go deep in the thermoelectric, but we have an overall idea where these kind of materials are used, how this kind of electricity is generated when we make the temperature difference there in the one and the other end, then we can generate the power. That is kind of thermoelectric material is working. The basic understanding we have here. Now, that means if you see in the nature or in the existence, all the semiconductor and the metal have the same approach. One end is hot, one end is cold, right? If you heat one end, other end will be colder, other end will be hotter. That means they all generate the electricity. And that's true actually. The all materials which in the existence of the semiconductor or the metallic, when you heat the one side, it's supposed to have a free electrons to travel. So that's why I'm not considering the insulators there. So if you heat one side, you will get easily to go the material to the other side heat, and then you can generate the electricity from there. Then why we are working on this field, like why talk about the thermoelectric materials as one of the approach, that section you will understand in this part. So this is the thermoelectric material which I showed you. So as I told, all the material can be thermoelectric material, but the performance of this material is defined as the figure of merit ZT, which is a sigma s square by kappa times T. T is the temperature, which is the operating temperature. S is the Seebeck coefficient, which I showed you in beginning, when you have a delta V and delta T, and the Seebeck comes from there, the coefficient. Sigma is the electrical conductivity. Kappa is the thermal conductivity. And thermal conductivity technically have a two part. One is from the electrons and one is from the phonons. So these are electrical thermal conductivity and phononic thermal conductivity. Temperature I consider here as a operating temperature. Now, the better the value of ZT, or in the other word is the higher the value of ZT, the better the material is. So if you need a good thermal power generation, you need a material which has a higher ZT. That is a very basic requirement. That means all material cannot be in this approach. The material which has a better ZT can only be work as a better thermoelectric materials. That's the very simple and the filtering out the most of the material from this approach. Now, our thrust or our approach is start here. We need to find a material which has a better ZT, or we need to make the material which can perform as a better ZT. So when I say we need to make such materials, suppose some materials are in the existence, then we do some structural engineering in that material and we make a better material of it and we get the ZT. So if you see very simple formula from here, ZT is sigma s square by kappa. And if I consider T as a operating temperature and I remove this T from here, like just for an example, we can consider there is a no T, right? So here, if you see the Z is proportional to sigma s square by kappa, that means mathematically it looks actually very easy. What does it mean? For higher the ZT, you need to increase the electrical conductivity, you need to increase the feedback coefficient, and you need a material which has a lower thermal conductivity because conductivity is down here. Temperature I am considering as a constant temperature where we are operating the device, right? So it looks very, very simple. I think there is no mistake here. It's very simple, right? But life in physics is not that easy when you go deeper in. What the problem comes here, these physical relations are such a interconnected to each other, which start destroying each other property and start disturbing the finding our dream for higher ZT. How does it work here? Suppose we need a higher electrical conductivity, right? So here, if we increase the electrical conductivity of the material by various approach, we will talk this approach later as well, then the electrical part of thermal conductivity will increase. That means thermal conductivity will increase actually, and this is what we don't want here, right? That's our first condition. We don't want this to increase. Now, if we see the second part, all right, we start increasing the electrical conductivity. Perfect. At the same time, this carrier concentration will also increase, right? So if carrier concentration is also increased, that means this part will increase, all right? If this part is increasing, that means Seebeck will start going down. So if sigma is increased or the some electrical conductivity increase, Seebeck will decrease, and this is what we don't want. We want it should increase, not the decrease. So that means these all three parameters are interconnected, which makes the problem more complicated and more interesting in same point of view. So at least for us, it makes more interesting. So that means there is no possibility to make it, but researchers has worked and they found a relationship here which we plotted with the carrier concentration, and they found there is a range of the time of the carrier concentration where you can actually find the better ZT, which is in this region. So this is what we usually do or try to make the material in this range of the carrier concentration, which looks easy but is not, but we will talk about it how is possible. So how actually it is possible we make on this particular material. So what approaches we use here, one of the very basic approach is the nano engineering. Of course, we do nano engineering in this. We tune the band of the material, band gap, which we call in general, so is a band engineering. We definitely change the structure of the material, their grain boundaries. So the grain boundary scattering also does happen. We also do the reduction of degree of freedom, or in this different way, I say we go towards the quantum approach of this material. And definitely the material science works in this case to design a new material using the various approaches such as data mining, machine learning, DFT. Those definitely we use those kind of approaches as well. One of the example I showed here is the way how the ZT was starting in 1940s and what happened actually in this region, in this era. So what actually is, excuse me, before the quantum confinement effect, which was reducing the degree of freedom, appears, the ZT was not able to reach until the 1 or the higher ZT, because always we had a lower ZT. But this only approach makes the ZT and increases too faster. So that's why since after the ZT has been increased and drastically going up. So this is one of the approach, but of course not in every case the degree of freedom works in this case. We have a different approaches to work towards that direction. And it depends on the material, what kind of material you are using it. Now, we understand what is thermoelectric, how it generates, what are the parameters, how we deal, and what are the approaches we work. Now the real business comes about the materials. What kind of materials are there? There are many kind of material which comes in the existence and the people are using. I will be talking about, first I will be showing about the material which I have worked and why I choose particularly those materials. And then I will be talking about one or two material in detail, what these materials are and how we are working towards that, and what results we got, and where we left the unfinished business at the moment. So when we choose the thermoelectric materials, the first basic questions comes in our mind. It depends on which temperature range we want to use those kind of material, or what application of that. Because in our research, we focus on the application first, which application we want to use that material. Then we start digging on that and make the device to work in that approach. So in my case, I have worked in the various kind of material, especially if I distribute this material, we come something near the room temperature and comes around 200 degrees C, which is the medium temperature range, and the higher temperature range more than the 500 degrees C, which I distribute here. So in this range, if I distribute, I start from number one, which is the oxide materials. These are very common, easy to fabricate, anyone can fabricate in the lab, easy to measure, anyone can measure it. These are known for the high temperature application here. And these are the one of the example I showed you where you use the car exhaust engine or you use the pot on the gas stove. These kind of materials are used there. Now, second is the chalcogenides, which is here, which I work on the tin cyanide. These are the medium temperature range, such as the direct sunlight and those kind of materials. Places you place these kind of material, which use around 200 degrees C and more. And the third I distributed here is the 345, which is these three materials. These materials, which I am working for the variable electronics, that means these all materials are used near the room temperature. So today in the presentation, we will be more details seeing these two materials. One is the oxide and the second is the halide perovskites. These two materials will be talking more and what we have achieved, what kind of devices we have made. So let's start with the oxide materials. So oxides are very easy to prepare. These are potentially low cost, I mean is cheaper technically, and these are non-toxic and stable thermoelectric material for the high temperature application or the application more than 500 degrees C. So we make the bulk P-type material as a calcium cobalt oxide. As you remember, we need both P and N type. So this is one of the example of the P-type material. So what approach we use, and we got a good result using the different approaches. We take the powder and we uniaxial press this powder, make a pellet. Then further we use the isostatic press, which put the pressure from all the four directions, and it squeezes well, and there is no, I mean, no is a wrong word, but there's a less porosity in this material. In this case, when we measure the XRD or come to know the phase of this material, we found the material is fabricated excellently without any trouble, without any problem. And what we were expecting, we got exactly the same. Then what we did in this case for the engineering point of view, what we did, we actually tuned the band gap and we increased more heavier element, which is as a part of the terbium doping here. These materials are the heavier and it goes inside the lattice and change the lattice points and work as an excellent thermal conductivity reduction element in our case. Then we make this kind of different samples here where we use the different doping. What accidentally we find the situation is we goes over the limit of the solubility or until where you can actually mix this material. Like suppose you are cooking something and there's a limit you can put, suppose the salt you are putting, there's a limit you can put the salt in that. You cannot put more than that salt. It will stop dissolving there, which is the solubility limit there. So in our case, we found the solubility limit was around 0.5 and 0.6. After that, if you see this peak start disappearing. So that's where the start changing the phase and the different phase start happening. So we stop over there and we saw how much response we get from this kind of material. We fabricate these materials and then we see the structure of this material where we found 0.5 shows the best, and this is the pure material. What we see here, we found a layered structure which shows the presence of terbium ion over here. In this case, when the presence of the terbium ion, it helps us to reduce the to increase the carrier concentration, which we will be seeing in the next lessons here. So when we work on that material, what we found is ZT increase and reaches around 0.75, if I'm not mistaken, is around 0.75 ZT in this work. And this is the best reported material for the P-type as a bulk material, which has ZT around 0.75 or zero point 0.8 about. And this was one of the best, I think this is still the best work. Nobody has reported more than this ZT yet. So what we understand during this project is the isostatic press helps in enhancing the packing density of the pallet. That means the grains comes closer together, they melt each other, and they perform better electrical conductivity in this region, or towards the one grain to the other grain. That's what we understand here. And the doping of terbium or the TB causes a reduction in relative concentration of cobalt 4 plus ion, which gives rise to the larger S while enhancing the phonon scattering. So what does this particular line means here? So terbium is a heavy element. So when you put this element, and I think in the masters you already have studied about, for the student especially, studied about the phonon scattering. So phonon scattering happens, phonon moves, and where the heavy materials comes is scattered from there, and that's what we are looking for, reduce the thermal conductivity. So terbium ions here helps in this case. When the phonon is coming towards it, it's break down that scatter that phonon, and the thermal conductivity increases. That's what happened in this material case. Thermal conductivity drastically goes down, but at the same time the Seebeck increases in the larger Seebeck increases because the overall carrier concentration, which was governed by SN4 plus, increases, and reduces, which increases the Seebeck coefficient in this case. And at the same time, the electrical conductivity of this material increases because the grains are highly connected, and these are melted grains kind of a structure, which I showed you in the previous slide. So that means all those three conditions which I showed you about the ZT works very well at there, and the ZT enhanced, and we have reported the enhanced ZT at this stage. And people has been working on this material since 2000, and 2016 we have reported this as a best thermoelectric with the terbium doping. Now, when we reported this, this has been covered in the many different international medias, including which one of the best I believe is the Wall Street Journal in our case. And this work was also Siege 1 patent in our case. This materials has been commercialized already. And this is the one thing about the material. So there we use the material which is in the bulk form as a P-type. I also work, or we also as a group working towards the N-type material in a thin film form. So these thin film form materials, what we use is, as I told in the beginning of the slide, we did the nano engineering or reduce the degree of freedom. So when we reduce the degree of freedom, the quantum confinement effects comes in the picture here, and this helps to increase the Seebeck coefficient. In this case, what happened is it was easy to do nano engineering. We will see why it is easy to do nano engineering in this case. And in thin film case, it helps you to deposit the film on the various shapes. I mean, bulk has a one particular shape. You can cut it, you can chop it, but thin film you can deposit on the various shape which you want to desire in this case. And these are light in weight also. I mean, bulk is a heavy. So that's what we start working on a thin film. So in the thin film case, what happens actually here, you have a bulk of the material and you transform this material as a thin film. This is the substrate and this is the film on top. So when we deposit this material and we see the ZT or the figure of merit of this material, what we actually found, the ZT has almost 5 times enhancement than the bulk material, and that is also another best reported result for the N-type thermoelectric material in the oxide case. There is another report recently came which we were talking. I think that is also the N-type. That is a P-type, but in the thin film. That is also very excellent. I don't remember the result, but it was also one of the best. This is still one of the best results for the N-type material. Then how we do actually that kind of engineering, which I talked, the nano engineering is easy in the thin film case. So in the thin film case, for fabricating this thin film, we use the pulse laser deposition technique. In this technique, what happens is you have a laser beam and you use a lens, which probably every of us has done in their childhood. We use a lens, and focus the sun rays there. So this is the same lens we use here, and we focus this laser beam over the target, which I showed you in the first. We have a bulk material and make in the thin film. The same target we mount here. When the energy of this laser confined in a very small area, so it generates the plasma of that material, or the plume, which we call, and deposit on the thin film as a form of the thin film on the substrate. And this process has been done in the high vacuum chamber, where you keep pumping this vacuum, and in oxide case we flow the oxygen in, so the complete environment inside is oxygen environment. So in this approach, while making the thin film, it's very easy to do the nano engineering to control the grain boundary scattering, and definitely we can do the band engineering. And obviously from the bulk to thin film form is helping in the reducing the degree of freedom. It become from 3D to 2D material in this case, or thinner 3D material where you have. Now this is one of the things, but actually how does this all happen in this case? So what we actually do is, if you see very small example here, this target which we are using it, we put some kind of a nanoparticle or the particles, microparticle inside this material of the different material, and then we deposit the film. So these different materials work as and grow as a nanorods here. Similarly, if we put a pizza slice here, or the triangular slice on the top of the target, and we deposit the film, we get these nano dots or the nanoparticle inside the film. Similarly, when we combine these two and we work two target here inside, we can achieve the film, which is this. So these all different kind of structures are working as a phonon scattering, plus these all structures helping you to tune the band gap of the material of the overall this material, which is the zinc oxide in our case. So these approaches we have used, and it is easy to use when you make a thin film in this kind of material, other than working with a bulk material in this case. So this kind of material we have shown, and we have reported the result where the thin film has achieved the better result than the bulk material. So that was about the oxide, what we have worked on the oxide and showed the result, how the oxide materials can be tuned and can make a better material as a higher ZT and can be used in the industry on the different application point of view. Now, that is the one part which I showed you. The second part, or the second material which I was talking here, is the halide perovskite. These materials are very recent and the new materials, and these materials are known for their excellent performance in the solar cell. And these materials can be written as the ABX3, which is one of the material I am working is CSSNI3 here. The beauty of this material is the material has intrinsically low thermal conductivity and high seebeck coefficient due to the presence or the structure of the making of the CSSNI3. These two property actually we have inside the material. So our goal is to increase the electrical conductivity, which we are working on these materials, and together with that keep the value better of the this seebeck coefficient value. This is the our approach we are working. But these materials which is reported for the so far in this point of view are for the single crystal. However, our approach is to make this film for the flexible device or the thin film form and transport it to flexible device. So we started working on these materials, and we used a chemical approach to make this kind of material, which is very simple. You use the precursor powder in the different solvent, and you spin coat this material. You use the anti-solvent, and you heat this material. So what it happens is here this is the condition up to here before the baking or the heating. As soon as you heat it, turn to the black material, and that's what we are looking here for the higher conductivity. Now, to optimize this kind of material, we had a baking temperature from 50 to 150 degrees C. Other parameters such as the baking time and the spin coating speed and time we kept as a constant here. So this 5 temperature we varied, and what we found here is, if you see the material which has grown for the 130 degrees C shows the best result in electrical conductivity. Similarly, quite similar result for the seebeck coefficient, and the thermal conductivity which need to be less, right? If you remember the formula from the ZT, it was sigma s square and kappa was the down here. This is a sigma, sorry. and T somewhere here. So you need a lower thermal conductivity, and if you see 130 has shown the lower thermal conductivity, 150 has also shows the lowest thermal conductivity, but this material has changed the form at 130, so we will not consider it here. 130 was the best material which we choose, and from here, when we calculate the ZT, which was the best ZT reported so far for this particular material, is around 0.14. And also, it's important to note this is the ZT for flexible material, or the compare with the organic material which they are making for the wearable electronics or wearable device. This is one of the best ZT material which we have got at the moment. Now, one thing is here which I miss or did not talk about is the power factor here. So this is the power factor. This is another property to compare how the material is, how much power it can actually produce. So power factor you can simply calculate by sigma s square, and ZT, if you remember, it is equals to sigma s square by kappa into T. Okay, so this part is actually the power factor. So why power factor is important? If somebody asks question this, I think people have this in mind. Why power factor we are talking? We already have the ZT in our case. Actually, in the experiment point of view and in the physics point of view, measuring the thermal conductivity of thin film is very challenging, or is extremely challenging actually, measuring the thermal conductivity of the thin film. So in that case, without measuring the thermal conductivity, by the value of power factor also you can predict how the material will respond. So if you have a better power factor, that means material will be better. That's why people plot usually the power factor as well, and that's what I also did in this case. So now go back here. So we got the one of the best ZT here for this material. So we have a best ZT, we have the material, we made it. So now what is the next step? Next step is we have to make the device. Then we made the device of this and generate the power from here and see what does it happen. So what we did is we used the substrate, and on this we put a mask from the Kapton tape, and then we put this precursor solution which is here. We heat it and it become turned black. We remove this mask from here, this Kapton tape, and we put another mask which is the shadow mask to make the electrical connection. And once we make the electrical connection, we can generate the power from here. There's the module. So we use here two kind of approaches. One is we deposited the aluminum and the copper leg, and one is simple, we just connect the copper wire with the silver paint. And when we do this, we make the module, which is this device, which is here. This is by the depositing of the aluminum, I believe, and this is the copper wire connected with the silver epoxy or the silver paint. So here what we did, we start heating one end of the module and the other end is cooling, and we generate the power, how much power is generating. The maximum output power we found is a 0.8 nano watt. That is for the 5 legs here, 1, 2, 3, 4, 5. So this is the for 5 legs. The power is less, but still it can be, I mean, with a further improvement, it can be used for the IoT devices, which I was talking in beginning. So that kind of devices can be used in this case now. What is the another problem we face here? As I showed you the module, it's supposed to have a one N-type and one P-type material, and then you start heating it, right? And other end you are cooling, and then you get the power value, sorry, the value of the current or the power here, right? That is the main module structure. But in here case, we have only one P-type material, which is CSSNI3. So if suppose it has an N-type material again here, so this will combine on the same chip, and the number of legs will increase in this case, and in P-type, the power will drastically increase in this case. So that is our main goal, which we are struggling now, and it's an open question to make the N-type material. We started making this N-type material, and we worked, which I call is towards the N-type material. So one of the very basic approach to make the N-type material or different type of material is to dope this material. So when you dope this material or the any material, you can tune their electrical conductivity, you can tune their type of carrier concentration, and you can make the N-type material. We tried here We doped various material on the various concentration, and Seebeck coefficient, we always got the positive. That means it is a p-type material, is not the n-type material. It always have a p-type. So that means this material cannot be transformed in the n-type material. The reason why is the presence of Sn here. When you see this material, it oxidizes from Sn2 plus to become Sn4 plus in this system, and this always results as a p-type material. But there is an approach. What if we change this material Cs from here and put some other material which helps in stabilizing this factor here for us, and we have a less Sn4 plus or no Sn4 plus, we can get the n-type. That is the physics or the core which is working behind our approach, how to find. So what we did, this is slide you saw before. We had started this material. So what we did is we changed this material with the organic component of here, which is CH3NH3, which is we call as Ma, methyl ammonia here. This is here Ma, we call it, which is called it MsCSNI3. I will be calling from now onwards this material. So we make this material. This material also have a very intrinsic property of ultra low thermal conductivity. That means their thermal conductivity is always near 0.1 or 0.6, somewhere between that, and that's excellent low thermal conductivity, and has a higher Seebeck coefficient. Electrical conductivity we need to tune as I expected in this material. So how we make this material? We take the precursor, we make the solution here, and we spin coat this material, we put the anti-solvent, and we get the material which we are looking for. Same approach as what we did before. So here, when you make this material, so one example I showed you about the doping, to where you can move towards the n type of material. There is another approach of tuning this carrier concentration, which is known as the schematic deviation. What does it mean is, so suppose you have a material MaSni3, which is here. This material is made with the schematic ratio of 1:1 here. But what if you change this ratio itself? I mean, the concentration, if I change, I can easily make it the N or P type material. So that's what approach I followed in this case, and I changed the schematic deviation here, and I will see what happens in our case. So XRD shows the excellence performance of this material. When we see the SEM image, it shows the nicely the grains are connected, their porosity has increased, but still is much better. Then here, porosity is increased. Then we measure the electrical conductivity of this material. What we found here, if you see, so okay, one point I missed. So the Seebeck coefficient, if it is positive, it is known as the P type, and when this coefficient is negative, is the N type. So what we see here, for this schematic deviation, we actually got the N type material, and that's what our planned work, what we were expecting from the schematic deviation and stabilizing SN2 plus and 4 plus by using the Ma element. So this was excellent, and it work was almost 1.5 year work we concentrated on this topic, and we finally able to make N type. But happiness doesn't go longer here also for us. What we did, we have to see how stable it is material actually. Then we start heating and cooling this material. So when we start heating this material, it start oxidizing again back on this temperature. This temperature range, it converted again the P type, and while cooling cycle is still as a P type. That means only schematic deviation cannot help in our material. We need to find other approach as well. So we are working on the next step, and here is the power factor of this material, where this is the cooling cycle power factor and this is the heating cycle power factor. So what does we take away question from here is, so sometimes we are working towards one problem with the one approach is not necessarily always it's solved from the one problem only. Like suppose in this case or the previous case, doping and the schematic deviation both have shown the signal of N type, but actually when we finally want to result as a stabilized material, it's not helping. You know, we are working on the next step and we got the result very positive. I'm sorry, I cannot show it here, but we combine some way these two approach together, the doping and the schematic deviation. This two material helps and stabilize the SN4 plus ion, and we got excellent result in the N-type material, which we are fabricating the device and further move to make the more device in this case. So I will finish here, conclude in the quick summary. So what we have done, we have fabricated the oxide and halide materials, demonstrated for the different operating temperature, heavy and enhance the phonon scattering and results in the lower thermal conductivity. Present of the different ionic state helps in enhancing the value of electrical conductivity. Hence, results higher for the ZT, which is about the oxide material. But on the other hand, growth of N-type halide perovskite was demonstrated. Still further improvement is needed to work towards this kind of material. I would like to thank for the funding agencies which I work, or the different institute which has supported for my work. And this is the group where I am at the moment. And thank you. I would be happy to take any question if you have.
Thank you so much, sir, for such an enlightening session. Yes, we have few questions from the audience. If you allow, I can ask the questions.
Sure, sure.
Sure. So, the first question is from Dr. Lokesh. How can we increase the efficiency of thermoelectric generator?
So in this case, I will say we need to, for increasing the efficiency, the very straightforward answer is to improve the ZT. And how to improve the ZT, that's what we are talking about, different approaches we use and increase the ZT of this material. And that's all I can say.
Okay, sir. So moving to the next question, that is by Poonam Daga. Can doped insulators decrease the degree of freedom and act as a thermoelectric material?
I
Hello.
think you mean to say is doped semiconductors. I mean, doped insulators. I don't think that there is anything I have heard about it. Doped
Okay, sir.
semiconductor are the one thing which you can talk about. I mean,
Okay.
insulator is, suppose zinc oxide, if you take, for example, that is intrinsic semiconductor and the conductivity is very low. But when you dope it, you can definitely change it. And reducing the degree of freedom, I mean here is, or in general is meaning, like suppose you have a 3D material, you change it to the 2D material. So that is not related with doping. So it's a structure of the material you are changing. So in my case, we have a bulk pallet, which is around 2 centimeter in the diameter and around 5 to 7 mm in the thickness. That I change it to the lighter one. Suppose I made a thin film of the 400, 200 nanometer. So that's how you change the degree of the freedom there.
Oh, okay, sir. I hope the query is solved because the Poonam
Hmm.
Daga, I think the participant has raised a hand. Uh,
Ah, okay.
okay, okay.
Ah, your chat box
So
I can
moving
see,
to the
yes.
next question. Okay. So
Yes.
moving to the next question, sir. What type of material? This is by Dr. Kriti Srivastava. What type
Mhm.
of material, N or P type, is more suitable for thermoelectric material?
Okay, so one material, I cannot say this as a full answer, but it depends on which temperature range you are seeing. So if I say at the moment in the commercial point of view, is bismuth telluride is one of the material which can be doped as a P and N type both and used widely as a commercially available thermoelectric material. The organic case or the variable electronics P dot PSS is coming in the picture now, and what we are working also on the paste or the screen printing of this material, but those are not commercially available yet. So at a particular one material, taking a name is difficult, but different temperature range you have different materials.
Okay, sir. So we have one more question from Jyoti Arya. What material is used to improve conductivity?
So what material is used to improve conductivity? So conductivity, I understand here the electrical conductivity probably you are talking about. And material, I mean, there are many material you can use for electrical conductivity, but probably, I mean, you want to ask what approaches are there to use can be for increasing the conductivity. In that case, you can use the doping. You can mix the different, like suppose what we are working on the halide perovskite, you can work on the dual halide perovskite. You can also input the different doping. You can use the band structure. You can change the band structure of the material. You can try to put the multi-layer of that material that can also works to change the electrical conductivity.
Okay, sir. So there is two more questions actually.
Mhm.
One is from Bhupendra Sharma. When increasing temperature, what is effect on conducting and non-conducting? Uh, I think the participant wants to ask the effect of increasing temperature onto the conductivity and conducting material and non-conducting material, I guess. Yes.
Okay. So, I mean, first thing is like when you need to work on the thermoelectric material, you need to flow the current, right? So that means we are always talking about the material which has a conductivity. It's not a conductor, but which has a conductivity. That means it can be semiconductor, it can be any other conductor. So those kind of material definitely with the increasing the temperature. So in the semiconducting case, with temperature, it will, I think, increase the conductivity, right? If I'm not mistaken, this is the R. So one by decrease the conductivity. So you will decrease the conductivity in this case.
Okay, sir. So there is one more question. Is there any biological application being targeted using thermoelectric material, for example, in thermal cycler for DNA amplification or any other thing?
Biological application. So I mean, thermoelectric case, biological application. There, if I'm not mistaken, there are people who are working on some biological point of view, but I do not remember exactly the material. The commercial material at the moment is bismuth telluride, which cannot be used like biological application because it's a toxic material. And the wearable electronics, what we are working. So, example, thermal cycle of DNA. No, I have no idea about that thermal cycling for DNA.
Okay,
So
okay, sir.
that I'm not sure. But the wearable electronics case, there are many material which we are working, and I showed you also P dot PSS. That is one material can. Sorry, the halide perovskite. That is one of the material you can use for wearable electronics, but not directly printed on your skin.
Okay, sir. Sir, I have one more question.
Mhm.
This question is from Pratibha Pal. Why people use P dot or P dot PSS? Is it helpful to the material stick on the substrate during spin coating?
So P dot is a material and PSS is a doping in this material to increase the electrical conductivity of the P dot. So that's why we always call P dot PSS together because that's a conducting material. I mean, when I say conducting means semiconducting material. Now, this material itself is a thermoelectric material. So this itself goes and stick on the substrate. So this material doesn't need as a glue for the other material.
Okay, sir. I hope the query of all the participants are solved, and thank you so much, sir, for such an
Thank you.
enlightening session. Now, taking the session ahead, I would like to invite Dr. Lokesh Gambhir for the vote of thanks. Over to you, sir.
Thank you. Thank you so much, Dr. Neha. Good morning, everyone. Rather, good afternoon, everyone. Every smart attempt is a promising feat in education. That's what we say here in our department, and that's what is our motto in Suresh Ganwar University. So we at School of Applied Sciences and Center of Renewable Energy and Storage, Suresh Ganwar University, are determined to bring eminence within the reach of our students. Uh, with the vision of holistic grooming, knowledge outreach, and scientific industrial mentorship, the present lecture series is being organized in the field of physics and renewable energy. With 16 different states of India and across the nations, and more than 300 participants being deliberated in this particular lecture series. It's a wonderful beginning. And with the wonderful beginning, I extend my humble, profound thanks to our keynote speaker, Dr. Shrikant Saini, for enlightening the session, sir. It was a wonderful deliberation and very insightful deliberation regarding the complex thermoelectric materials. Thank you so much, and also thank you so much for taking out the time in very short notice. And also, I know that you are suffering from mild fever. I hope that I wish you a very speedy recovery and a very good health. Thank you so much for taking out time. I extend my profound gratitude to the honorable management of Suresh Ganvia University for providing generous support for the lecture series. I extend my humble thanks to our sponsor, Soft Material Research Society, Jaipur. I would like to thank Professor Gaur Sharma, Principal, School of Applied Sciences, for his motivation and continuous encouragement. Further, a special thanks and gratitude to Professor Ankur Jain, Coordinator, Center of Renewable Energy and Storage, for eminent collection of speakers and providing us the platform and the collection and the contacts to organize this particular lecture series. I extend my thanks to Dr. Neha Kapoor for wonderfully coordinating and moderating the session. A special thanks to all the faculties involved in coordinating the streaming of lecture in the seminar hall. And lastly, a very special, delightful thanks to all our students and the participants who registered and joined the session. It's your enthusiasm and zeal to learn which actually drives us to organize these events. In line to the series, the next lecture in the series is scheduled on 28th December 2021, which will be delivered by Dr. Dayanand Kumar from National Kang University, Taiwan, on artificial electronics and apps. We look forward for your presence in the second lecture. With this, thank you so much. Thank you so much. And I know I have a request of presentation slides. So it's up to Dr. Shrikant, sir. If you can give us the slides, then our students as well as the participants will be very helpful with it. Again, thank you with your ease of conducting the lecture and providing us your time. So with this, I hand over the platform to Dr. Neha Kapoor for the concluding remarks. Dr. Neha, if you may please.
Thank you so much, sir. Thank you, Dr. Shrikant, sir, once again for delivering such an insightful and informative session. Now we shall, I shall call this session closed, and there is an announcement for all the participants that the feedback link for the session would be shared via mail that you have to fill by today only. Thank you so much, everyone, for joining. Thank you so much to Dr. Shrikant for once again for delivering this talk. Thank you, everyone.
Thank you.
Have a nice day.